Okay? The last isomer is probably the hardest one to visualize. And really, there isn't too much that's different about most of these complexes. And these are called optical isomers. I'm going to say a couple things about these isomers. Optical isomers are defined as non-superimposable mirror images. And what happens in optical isomers is these isomers rotate a plane of polarized light in opposite directions. Another thing that we can say about these optical isomers, these complexes are called chiral compounds or enantiomers. And the reason I bring this up is because if you're taking organic chemistry, this is one of the first things that you're going to talk about. Chiral compounds or non-superimposable mirror images. Okay? So the first thing you might ask yourself is, what the heck does he mean by non-superimposable mirror images? And this comes down to visualizing things in 3 dimensions. Okay? Yeah? Enantiomers. So if you talk to an organic chemist, they probably aren't going to refer to this as optical isomers. They're going to refer to these compounds as enantiomers. And I would suggest reading up on this in this section of the book, and it's going to show you like this picture of a hand and then your hand in the mirror and trying to superimpose those two on top of each other, and it's not going to happen. Okay? Well, that would kind of be nice if we talk about hands. And I think in one of the example problems, it asked about a shoe and a loaf of bread or something like that, right? But we're not talking about shoes and hands and loaves of bread. We are talking about coordination complexes. So the first thing that I want you to keep in your mind here, and the examples that you typically see of compounds that have optical isomers are Ml4 tetrahedral molecules, where L is 4 different ligands. You can also have Ml6 compounds. Ml6 compounds are all going to be octahedral complexes. Here we have an octahedral complex where L is 6 different ligands. Or we can have a case where L is equal to 2 bidentate ligands. We'll talk about what they are in a second. And 2 monodentate ligands in a cis arrangement. Or we could have an octahedral complex where L is equal to 3 bidentate ligands. And what a bidentate ligand is, instead of attaching at one vertice, it's a bigger molecule that occupies a larger space. Like, for example, ammonia has 1 nitrogen and 1 lone pair on it. There's a molecule called ethylene diamine, which is a much bigger complex that has 2 nitrogens on it. Those nitrogens have 2 lone pairs where when it forms a bond with a transition metal complex, instead of just occupying 1 vertice in the octahedral molecule, it actually takes up 2 of them. We'll talk about this a little bit more probably on Wednesday, but I want to bring up another point here, and that is, how do we visualize or draw these optical isomers? Because optical isomers are the exact same compound. It just so happens if we shoot light at that, and not just light, something called plane polarized light, it will be rotated in different directions. So this was probably one of the isomers that was discovered after everything else was, because it's kind of like a little nitpicky, tedious type of a thing. So the first thing that I want you to know how to do is draw a mirror image of each of these compounds. Yeah, is there a question? Two bidentate ligands and two monodentate ligands. So the first thing you have to do, and the way I would set these things up, is number one, is draw the parent structure without the ligands. And then after you have that, the second thing you want to do is you want to draw the mirror image. And the third thing then would be to add in the ligands. And what I mean by that is the following. If you have a tetrahedral molecule where I have my transition metal center, I'm going to have 4 bonds to that. 2 of them are going to be in the plane of the page. 1 is going to come out of the page. 1 is going to go back into the page. Draw that parent structure. Then draw what its mirror image would look like. So typically we use a mirror and we draw it kind of like this. We're going to have the transition metal center, and the 2 bonds in the plane of the page are easy to kind of draw in here, where it would be like looking into a mirror. If this metal complex right here was looking into the mirror, it would see something like this on the other side. Then this bond right here would come out of the page, and there would be a bond going back into the page looking like this. So this is kind of like your parent structure in the mirror. If I have a ligand that will denote as X, and 3 ligands that will give as Y, the mirror image of this would be X up here at the top, then Y down on each one of these 3. So the question we need to ask ourselves is, can I take that mirror image drawn over there on the right, and can I pick it up and rotate it around to superimpose it back on the original molecule? And what I need to do in this case is, if I was looking in the mirror at this molecule right here, I could grab the molecule right here at X, and I could just rotate it, and it would fit right on top of this other molecule right here. So if I pick that up where I circled X, and I rotate it just a little bit, I can superimpose that or place it directly on top of that other molecule. So there's no optical isomers here. Okay? But on the other hand, I said one of the examples here would be an Ml4 tetrahedron where L is 4 different ligands. So let's just say I have my transition metal center, and I draw the tetrahedron just like this. I set up my mirror plane. I have the mirror image here where this bond comes in here like this. This goes like this. I have a bond coming out and one going back into the board. Again, we first draw our parent structure, then we put the ligands around it. So let's just say I have ligands A, B, C, and D. Now I have to draw the mirror of what that would look like. So A is still going to be up here on the top. B is going to be closest to the mirror. C is going to be over here on this side, and D is going to be the one out here in the back. Now the question is, can I pick up the mirror image, rotate it around, and superimpose it right on top of the other one? If I do this, I can superimpose A right on top of each other. So I'm going to pick this up, move it over to the other side. A matches up perfectly. The question is, can I rotate this around so I can put B, C, and D on top of each other? So let's just say I'm going to rotate this where I'm going to make B be right on the same spot. So if I rotate this, then I have to take C and D, and hopefully they'll match up on each other. But when I do that and swing this around to rotate it so that A and B correspond to this bond right here, I'm going to swing it around, and C is going to come over here to the back, and D is going to be out on front. So what I can say about this particular molecule is it's non-superimposable on its mirror image. And if we have a non-superimposable mirror image, that means we have optical isomers. And this fits into the first example that I gave up here, where you have an Ml4 tetrahedron where you have 4 different ligands. Yes, Zach?
I just can't see, like, why couldn't you just flip that and kind of, like, match up? Like, it looks like you just flip that, like, all the way.
But the only way to match up A and B would be to take these right here and flip them around like this. Okay? So if I'm looking at you like that, right now, the hand that I have with this pen in it is pointing towards you. If I rotate it around like this, my hand is now back here in the back. Okay? So when you do that rotation, C and D, you have C coming out of the board and B going back into the board. When you rotate it around, A and B match up perfectly, but this changes, and C and D are kind of flipped. So we can't superimpose them on top of each other. In the previous case I gave right here, Y is all 3 of those molecules down there in the plane. So when we do that and we flip it around, if these 2 ligands right here are the same one, then it'll match up fine. Okay? But since you have 4 different ligands on there, it doesn't match up the way it needs to be superimposed on itself. So that's what we call optical isomers. Like I said, you really need to sit down and look at these with the structures, and there's a lot of 3D programs that I can give you links to online that you can kind of see how that works. But that's kind of the process that you have to do for optical isomers. And one of the things I would highly encourage is that you draw these things out. Okay? So these are the 4 different categories of isomers that I'm going to have you be responsible for in this particular class. Like I said, when you go on to take organic chemistry, or if you take an inorganic chemistry course, they'll go into a little bit more detail. But this is the foundation that I want to set for this particular class.